Hello, we're Group U, and our project was the experimental determination of a lift coefficient of a 3D printed airfoil. So our project objectives, currently the only way to determine the coefficient of lift is through experimentation. So the goal of our project was to develop an experimental test setup to confirm the coefficient of lift of a known airfoil design. And we plan to do this by using 3 Arduino compatible hot wire anemometer wind speed sensors to determine the coefficient of lift of our airfoil. So our test setup uses 3 airspeed velocity sensors, and these sensors were placed in front, above, and below the airfoil. And our test measured the wind speed above, below, and in front of the airfoil at 4 different speeds, 30, 40, 50, and 60 feet per second. So these are a picture of our sensors. They're approximately 2.5 inches long, and these are compatible with an Arduino. So that is how we controlled and measured the wind speed in the wind tunnel. This is a picture of the cross section of our airfoil that we got from a website for model plane builders. Here's an example of our test stand that is placed in the wind tunnel, including the white airfoil on top and the base stand that it is attached to. So this is an example of our entire test setup. You can see our 3 wind speed velocity sensors placed above, below, and in front of the airfoil. And it includes our airfoil connected to our test setup. And our airfoil is at approximately a 0 degree angle of attack relative to the wind coming towards it. So this is an example of our wiring for this project. We made use of this Arduino Uno to record data from our sensors.
Some of the strengths of this experiment were that the sensors are cost effective. They're approximately $25 each. The governing equation studied only relies on 3 wind velocities, so you could use the same sensors to figure that out. And then most of the parts that we use in this were all 3D printed, and you could just grab the CAD models off of our airfoil, for example, from online. Limitations for this would be our sensors was a big limitation. They were very inconsistent, and this is probably due to how cheap they are. For what they were doing. Most of these sensors cost like in the hundreds to thousands of dollars to actually read wind velocities. Turbulent airflow was another limitation in our wind tunnel. It is quite small and the scale of everything. So in order to use our sensors, we had to have a lot of things blocking proper airflow. And then the visualization that the wind tunnel, we didn't have any smoke to actually see the proper airflow of over our airfoil.
So for the uncertainty analysis, we used our governing equation, which was, we took 2 equations from NASA and we were able to simplify them down into this form to get our lift coefficient, which is CL. And that involves the upper velocity minus the lower velocity of the wing over the velocity in front of the wing to find our lift coefficient. So we used the equations we learned in class to calculate our uncertainty equation here. We found that the uncertainty of the lift coefficient was 0.0864, which gave us a total uncertainty of about 28%, which wasn't too good, but we accounted that mostly to our sensors and the limitations they provided, as mentioned above. And so this is the CL versus alpha, where alpha is the angle of attack plot that we took from the same model airplane website that we used to get our cross-sectional dimensions for our airfoil. And here you can see that our theoretical lift coefficient value for an angle attack of 0 is about 0.28, and our calculated lift coefficient data from our trials was about 0.3. And when we do the math, we find out that we were only about 8% off from what we're supposed to get from the table.
This is the design of experiment. We've created a 3x8 matrix of all the different possibilities of things that could be tested. When performing these are all variables that can be changed to give more or less accuracy. Angle of attack is one of them. So the high option is to have it angled up so that the wing generates more lift. Otherwise, flat is the low option for sensor distance. The high is close, low is far. Close meaning vertically very close to the top of the top or bottom of the airfoil. Far meaning further away, and then sensor location being forward or back is what we're trying to see there is how much wind is being affected by the airfoil before it reaches the sensor. So when you have it forward in the wing, it's rather undisturbed, but once you get further back in the wing, there's a much greater difference in the velocities.
And this is a picture of our final design of the experiment, and then a video showing it running.